Hello everyone, and welcome to Ryan Explains. My name is Ryan, and today we are going to talk about science and its imposters. So to start off this conversation, we have to first understand what science is. So you've likely heard of numerous fields of science before: biology, chemistry, astronomy, physics, neuroscience, etc. But what do all of these fields of science have in common? What makes them scientific? What separates science from its imposters? So if we type into our handy little search engine, what is science, we will likely get something along the lines of: science is the methodological approach to understanding our physical world through observation and experimentation. So that might sound like a lot, but it really just means that science, by nature, does two things. One, it follows a step-by-step methodology. And two, it aims to explain things in the world around us. So let's take a look at this methodology. If you've taken an introductory science course, whether high school or college, you've likely heard of what's called the scientific method. The scientific method is this step-by-step process in which scientists supposedly follow to learn more about the universe. So this scientific method starts with, naturally, an idea or observation that the scientist wants to explain. Then we move into the scientist formulating some sort of testable explanation for this observation. They call this a hypothesis. From there, the scientist would make some sort of prediction on what an experiment would tell them, assuming their hypothesis is correct. That leads us into the scientist actually planning and conducting an experiment. Now, this experiment can range in the field that you're in, whether it's chemistry mixing chemicals, or astronomy running simulations, or looking at the stars. It doesn't matter, these experiments can take all sorts of shapes. But based on the outcome of the experiment, there's two options. One is that their hypothesis is validated. In other words, their prediction is exactly their conclusion of their experiment. In this case, we want to make more predictions. We want to further validate our hypothesis. We want to make more predictions and run more experiments. But if instead our experiment does not validate our hypothesis, in other words, our experiment's result doesn't match our prediction, we should revisit the hypothesis and form new explanations that we can test. So this methodology might seem a bit complex if you're not familiar with it, but I promise you it's not too foreign. In fact, you've likely gone through these steps before and just didn't notice that you were indeed practicing science. For example, imagine that you cannot turn your TV on. You've been pressing the power button on the remote several times now, and the TV will not turn on. Well, perhaps you didn't think of it like this, but maybe you formulated a hypothesis that it is because your batteries were dead in the remote. Now again, you might not have thought through these steps, but you would have made some sort of prediction about an experiment. For example, if you get up and press the power button on the back of your TV, it should still turn on, right? Assuming that the hypothesis is correct, that just the batteries are at fault. There's no reason the TV shouldn't turn on by pressing the power button. Now we run through that experiment, we press the power button, and the TV turns on. Hooray, that validated our hypothesis. We could sit down, enjoy a snack, and watch our favorite show, but this doesn't mean that our hypothesis is correct. Later in the day, we go out and buy new batteries and put them in our remote. Well, that's another prediction, that if we put new batteries in the remote, it'll turn on the TV. Now, to our frustration, when we press the power button, it might not turn on our TV. This would falsify our hypothesis that the batteries were at fault. And now we would need to formulate a new explanation. Perhaps the remote itself is broken, or there's some issue with the connection between your remote and your TV. Again, these are things that we can test. We can buy a new remote or recalibrate the connection sensors. Now, like I said, you might not think through this process, but you've certainly gone through an example like this. Now, in science, an interesting issue comes up of when do we actually give up on a hypothesis? For example, if you went to your battery drawer and you put the new batteries in your remote and it didn't work, it could very well have been that the new batteries that you put in weren't actually new, or that they were faulty, or perhaps you just put them in incorrectly. It could have been another variable other than what you were testing. Now, if you just simply went to your hypothesis and made a new one saying, I should buy a new remote, and you do that, and the new one works, no harm done, but you never truly learned what was wrong with your old remote. So the question comes up of, when do you actually give up on a hypothesis that is seemingly falsified? Now, this doesn't just happen with TV remotes and old batteries. This happens in true science as well. For example, after Uranus was discovered, scientists said that they could use the laws of motion and gravity that Kepler and Newton gave us, and could make predictions on where the planet should be at any given time. When they did this and they looked up to find Uranus, where they predicted it should be based on the laws that we knew, they were dismayed to say they didn't find it. Our scientific method says that since the results of the experiment, looking for Uranus, didn't match our prediction of where it should be based on the laws, we should throw away the laws and make new theories on how motion and gravity work. These laws of motion and gravity, though, were pretty well established at the time, so some astronomers like John Couch Adams and Urbain Le Verrier didn't want to give up on them so quickly. Instead, they predicted that perhaps some other mass out there was disrupting Uranus's orbit, and this would actually work in with the laws that we knew of at the time. Much of the scientific community actually wasn't well accepting of these ideas. Both John Couch Adams and Urbain Le Verrier, who made these predictions independently, went to their respective observatories and were denied research time. In fact, it wasn't until Johann Gallet in the Berlin Observatory actually used the telescope there to look for this unknown mass that their theories were actually validated. He found the mass within minutes of looking up at where they told him to. This proved that the irregularities in Uranus's Neptune were not caused by faults in the laws that we knew of, but instead based on an unknown variable, some literally unidentified mass out there. This mass became what we know of today as Neptune, and is indeed one of the planets in the solar system. So you can see here, if everyone just gave up on Newtonian physics right away, we would have had a hard time ever finding Neptune, and frankly, ever explaining the odd motion of Uranus. But years later, a similar issue came up with the orbit of Mercury. Its orbit, over a very long period of time, actually shifts its alignment. This precession was nowhere to be found in Newtonian physics. Now, some astronomers, like, for example, Urbain Le Verrier, who helped find Neptune, said there must be some alternative mass that we aren't looking at. He proposed some unidentified planet between Mercury and Venus that was causing this disruptance. This planet, called Vulcan, was never discovered, and it would take until Einstein came around to explain why Mercury's orbit was so strange. It was because Newtonian physics couldn't explain it. Instead, Einstein redesigned how we thought of gravity, explaining that it was caused by curvatures in space-time from large masses. This meant that since Mercury was so close to the Sun, its orbit behaved relatively strangely. So, in the case of the search for Vulcan, we needed to throw away the old laws, or at least expand on them, to truly understand what was going on. So, an inevitable question comes up of, when do you throw away, or at least expand upon, a hypothesis or theory when you're facing seemingly falsifiable evidence? And unfortunately, there really is no good answer to this. Historically, it seems that There usually is two groups of people when facing seemingly falsifiable evidence for a theory. One group who sticks with the theory and tries to find those external variables, and one group who tries to expand or replace the theory with a new one. But as you can tell from our examples, both of these schools of thought can lead to further expansion of science. So enough about that. You understand at this point what science is. But do you understand what science isn't, or why that isn't science? Based on what I've said so far, you might assume that science would be something that follows the methodological approach that we mentioned, and things that aren't science don't follow that approach. That seems like a good way to put it, but there's an issue. Some discoveries historically in science have been miraculous, been found by pure chance. For example, the discovery of Uranus, whose odd orbit we just talked about, actually happened by chance. But that doesn't make it any less scientific. And this is a known problem in what's called the philosophy of science. If we agree that some sciences don't always follow this methodology, what's to decide what that doesn't follow the methodology is and isn't science? And this issue in the philosophy of science is known as the demarcation problem. This problem, in its core, is simply trying to distinguish science versus non-science with a simple criterion. An important note here is that philosophers of science and the demarcation problem aren't really too interested in distinguishing science from non-scientific fields. What I mean by these are fields like art or history or linguistics. These are fields that don't follow the scientific method, they don't need to, they have their own processes, and they're perfectly valid fields. Instead, what the demarcation problem is truly interested in are the fields that pretend to be science, the imposters of science. This typically includes things like fraud, like Andrew Wakefield's fraudulent claims of links between autism and vaccinations, along with nitpicking and denial, like climate change denial, and finally also pseudosciences, like creationism, the study of UFOs, cryptozoology, channeling, flat earth theory, hollow earth theory, etc. So this is really the core of today's video. How do you distinguish science and its imposters? So a famous philosopher named Karl Popper published a book called The Logic of Scientific Discovery, and in that book he proposes an answer to the demarcation problem. He says falsifiability is this criterion that sciences need to meet. What he meant by this is, for something to be scientific, it must be falsifiable. There must be a way to falsify it. And if there's no way to falsify something, there's no way it can be scientific. This means that using the blanket excuse of evidence being put there to test us cannot be scientific. And this falsifiability idea seemed good at the time, but it wasn't very long until another philosopher, Larry Loudon, argued that it did not solve the demarcation problem. He said this is because things like fraud and denial that are indeed falsified can still claim to be science. They can just claim to be bad science. Well, this isn't what the demarcation problem was looking for. They want to separate denial and fraud from science. So, while falsifiability may separate science from some of what is not science, it does not separate science from all that is not science. And that is a key point in the demarcation problem, and why it's still not solved today. So if you've made it this far and haven't given up on the video yet, you might be wondering, who cares? Why do we need to solve this demarcation problem? Why do we need to be able to philosophically distinguish science from its imposters? Even if we all intuitively understand what is and isn't science, why do we care about philosophically defining that? And the fact of the matter is because a definition of it would have great impacts on both education and public policy. For example, in recent years, many self-proclaimed creation scientists have put forth lawsuits trying to get creation science taught in secondary education as an alternative to evolution in science classrooms. Now, most of these lawsuits have actually been settled by the courts ruling in the side of science, by following Karl Popper's ideas, by saying that since creationism can't be falsified, it is not science and can't be. But this falsifiability does have its limitations. Like I mentioned, falsifiability does lack in some areas. Falsifiability can't settle what is falsified science and what is falsified non-science. For example, a scientist going through a rigorous approach trying to understand a phenomena and falsifying a scientific hypothesis is still largely considered scientific, even though the hypothesis was falsified. This is because they were following scientific processes. However, for example, the flat Earth theory, which has been falsified for thousands of years now, and simply nitpicks or denies evidence in the contrary to it, even though it is falsified, and even though some people claim it to be science, it is indeed not science. So understanding and developing a true criterion to what is and isn't science is important for education and public policy. And where are we with this today? How is the scientific community so quick to say what is and isn't science? Well, today scientists understand that scientific knowledge is provisional. In other words, falsifying data or evidence can in fact disprove a hypothesis, and you'd have to formulate a new one or expand on the old one. Now, when you listen to people from the Flat Earth Society or creationists, you often hear them say that nothing will change their mind. This is not scientific. That can't be. It is not understanding that science is indeed provisional. Another important thing in science today is peer-reviewed articles and journals. A scientist will spend months and years after they've actually conducted their experiments and gathered their data to develop a coherent and well-presented article for publication. After publication, these articles are rigorously reviewed and examined. Everything from the methods of collecting data, the data itself, and how it's analyzed are all reevaluated by other scientists and many other scientists. And lastly, many sciences revolve around the idea of theories and results being able to be replicated. This is true in the medical sciences. For example, not being able to replicate the connection between vaccines and autism that Andrew Wakefield proposed was an important reason on why it was rejected from the scientific community. So that's where we are today with distinguishing science from its imposters and why we need further look at this demarcation problem. And I would love to hear your guys' thoughts on this, so comment down below your thoughts and ideas on how to explain the demarcation problem, possible solutions to it, and anything else you'd like me to cover in more videos. If you like this video, feel free to give it a thumbs up and subscribe if you want to see more. Thanks everyone, have a great day. The disruptances in Uranus's Neptune, Alright everyone, that's all for this video. Or